Really fascinating challenge in the world of material science, how we actually characterize nanoparticles. You see, when you scale materials all the way down to the nanometer level, standard microscopy just kind of falls short. We really need some highly specialized analytical techniques to truly see and understand these structures.
Think about it for a second. How do you measure something that is 1,000,000 times smaller than a grain of sand? The wavelengths of visible light are literally just too large. They wash right over atomic-level structures. So we need a tool that operates on that same incredibly tiny scale. And that is exactly where X-ray diffraction, or XRD, comes in as our ultimate high-tech solution to interrogate the fundamental building blocks of these nanomaterials.
Okay, let's dive right into this. What you're looking at is our complete map of XRD characterization. It looks like a giant puzzle right now, but don't worry, we're going to decode this workflow step by step. We'll trace the entire process from the core physics, through the physical machine itself, and finally into the math used to extract all that actionable data.
Here is our roadmap for the journey today. First, the principle of Bragg's law. Then, from sample to scanner, decoding the XRD output, calculating size and strain, and finally, best practices and limitations.
Let's kick things off with Section 1, Principle of Bragg's Law.
So, the whole foundation of XRD boils down to Bragg's law. Picture this. An incident X-ray beam comes in, hits the atomic plans of your crystalline nanoparticle, and scatters. Now, if those scattered waves happen to align perfectly in phase, crest to crest, trough to trough, they amplify each other. That constructive interference? That's the underlying magic that the instrument ultimately detects as a diffraction peak.
And this whole interaction is beautifully summed up by the famous equation n lambda equals 2d sine theta. Constructive interference only happens when the path difference, which is that 2d sine theta part, is a whole number multiple of the incoming X-ray wavelength, n lambda. By measuring that diffraction angle, theta, we can calculate d, and d gives us the precise interplanar spacing of the crystal lattice.
Moving right along to Section 2, from sample to scanner.
So how do we actually prep a sample for this machine in the real world? Well, if your nanoparticles are swimming around in a colloidal solution, step 1 is to dry it out. Step 2, you carefully collect the resulting fine powder, and honestly, that's your gold standard for X-ray. Alternatively, step 3, you can create a thin film by drop casting or spin coating your sample onto a substrate. The absolute critical rule here, you need a highly uniform layer on a low background material so you don't mess up your X-ray readings.
All right, once prepped, the sample goes into the instrument. Let's track the journey of the beam. It originates at the X-ray source, usually a copper K alpha tube, and passes through a divergence slit to really focus it. This beam then strikes our sample, which sits on a rotating platform called a goniometer. As that goniometer spins, the detector moves along an arc, picking up the diffracted X-rays at various 2 theta angles. It requires some incredibly precise synchronization between the source, the spinning sample, and the detector to pull this off.
Now for the results. Section 3, decoding the XRD output.
So what does the machine actually spit out? You get an XRD diffractogram, plotting intensity on the vertical axis against the 2 theta angle on the horizontal axis. Each one of those specific diffraction peaks corresponds to a unique atomic plane, and it's a massive treasure trove of structural information. From these simple peaks, we can extract phase identification, determine the precise crystal structure, calculate the crystallite size, measure lattice strain, and even evaluate the overall crystallinity and defects in the material.
Let's get into the math. Section 4, calculating size and strain.
Now, what's really interesting about this slide is how we extract actual physical dimensions from our raw data using 2 distinct mathematical models. It's super important to keep them separate in your mind. We have the Debye-Scherrer equation, which is laser-focused on solving for the mean crystallite size. And then we have the Williamson-Hull method, which solves for microstrain, also known as lattice strain. Let's break down exactly what each formula is trying to uncover.
Let's look at Debye-Scherrer first. D equals k lambda over beta cosine theta. Here, D is our mean crystallite size in nanometers. K is a shape factor, usually around 0.9. Lambda is our X-ray wavelength, and theta is that measured Bragg angle. But the VIP variable here is beta, the full width at half maximum, which is basically how wide the peak is. Because beta is sitting in the denominator, there's a crucial inverse relationship. As peak broadening goes up, the crystallite size goes down. But simply, wider peaks mathematically mean smaller crystals.
But what if your crystal lattice is a bit stressed out? For lattices exhibiting microstrain, we bring in the Williamson-Hull method.
This equation builds on the last one by factoring in lattice strain, represented by epsilon. By plotting this out as a line graph, specifically for sine theta against beta cosine theta, this method brilliantly separates size-induced broadening from strain-induced broadening. Looking at the plot, the slope of the line gives you the strain, and the y-intercept hands you the crystallite size. Pretty neat, right?
Okay, aside from the dimensional math, we also need to know what material we actually made. Enter phase identification, or the search-match process. It's kind of like dusting for fingerprints. You just take your measured XRD pattern and compare it against standard, known databases like ICDD or JCPDS. By matching your mystery peak positions and intensities to these established standards, you can positively identify the exact phase of your synthesized material.
Time for a reality check in Section 5, Best Practices and Limitations. Let's contrast our ideal setup rules against some hard physical limitations in the lab. For best practices, you always want to use a well-dried, fine, homogeneous powder. It's also absolutely crucial to remove any instrumental broadening by using a standard reference, like silicon, and to use the appropriate 2 theta range and step size for your scan. But we have to acknowledge the limitations. XRD gives you crystallite size, which is often smaller than the actual physical particle size you might see under an electron microscope, especially for polycrystalline stuff. Also, if your particles are ultra-small, like under 2 nanometers, or amorphous, you're not going to get sharp peaks. You just get these broad, blurry halos.
So, zooming all the way out, why does this actually matter? Well, determining crystal structure, phase purity, defects in strain is exactly how we control the quality of the nanomaterials we're synthesizing. This structural data literally dictates the macroscopic optical, electrical, and magnetic properties of a nanoparticle. It's a real game changer. Mastering XRD is absolutely essential for driving forward both academic research and advanced tech applications.
Bringing it back to where we started, look at our complete map again. The logic of the workflow should be crystal clear now. From the physics of Bragg's law on the left, moving through sample prep and the scanner, and straight into the data analysis and math on the right, this is the comprehensive framework. You now have a really solid understanding of how to read and apply every single section of this complex chart.
The sheer power of XRD lies in its ability to take the invisible atomic structures of our world and decode them using just a single beam of X-ray light and some robust math. It completely transforms the infinitely small into measurable, actionable data. You've got the tools to analyze these foundational structures right here. The only question left is, what will you discover next? Thanks for joining me on this explainer, and keep exploring.